Hi, I'm Bryan,
And I am Hopkins.
and this is our E&I final project. This is our charging circuit. The purpose of the charging circuit is to be able to charge a 1.5 farad 5-volt capacitor up to 5 volts from the solar panel rail, whose voltage is supplied by the 9-volt solar panel. This charging circuit is important for the rest of our circuit, as it is responsible for powering all the rest of the circuits in our system. When the solar panel is removed, i.e. during nighttime, the discharging capacitor is responsible for powering both the illumination circuit and the charge monitoring circuit with the remaining power.
The purpose of our first circuit, which is the charging circuit, is we want the solar panel to charge our capacitor up to 5 volts, but then we want it to autonomously stop. But there's a problem because our solar panel has 9 volts, so we have to fix a way for it to stop charging once it hits 5. So, the idea is that we used a comparator. And so, there's one basic rule behind a comparator, and the comparator has this rule that V plus is greater than V minus, shown by these pins, will be on if V plus is larger than V minus. And this is the output. So the output is on when V plus is larger than V minus. So, the other rule is that the opposite. If V plus is less than V minus, output will be off. So, how do we handle this? So, we have a solar panel connected to a 2.5 volt diode, which basically means that when the solar panel is running through the diode, it only emits 2.5 volts. So, at this V plus, we have a constant 2.5 volts reading into the comparator. And then also, we have this solar panel charging the capacitor down here with a voltage divider in mind, so that we have, once the capacitor is fully charged to 5 volts, this will read 2.5 volts as well. But if the capacitor were to go over 5 volts, this would read V minus is over V plus. And that can't happen. So, once the capacitor is fully charged to 5 volts, this will shut off, and the output, by this rule, will be shut off. And then we go over to our circuit.
And so you can see here that we have we're expressing a light going into the solar panel, which is going through these wires into this rail here. And so what this rail does is that it expresses here's the diode, so we have the solar panel voltage going through the diode and out through this yellow cord into the third pin of the comparator. So with this, it goes in through the diode, and so it constantly reads 2.5 volts in that third pin. That third pin is V minus. So the voltage of the solar panel also goes through. Where else does it go? It powers the comparator from the white to the yellow to the purple, and that's where the comparator gets its power source to work. So we have the output of the comparator connected to the base of this transistor, which also acts as a switch. So with the V minus reading 2.5, as you can see the voltage divider here with the gray wire connected to it going to the second pin, which is V plus. So we have the divider, as you can see, with this gray line, with the gray wire, going from this voltage divider, which cuts the voltage in half into the reading of the comparator. So with this constant voltage at 2.5, once this reads 2.5 at this pin, the entire comparator shuts off and it stops emitting extra voltage into the capacitor right here. So at that point, it has 5 volts, and no matter how long we leave the solar panel going into this comparator, the comparator won't add voltage to the capacitor.
This is our illumination circuit. The purpose of the illumination circuit is to be turned on when it is nighttime, i.e. when the solar panel is not connected and the circuit is running on the capacitor voltage. During the night, when the solar panel is not connected, the white LED in the illumination circuit is supposed to light up from the power supply by the capacitor, whereas during the day, when the solar panel is connected, the white LED is turned off. There is also a switch that enables the user to turn the LED off, and a knob which enables the user to control the intensity of the LED.
Okay, so the second part of our circuit is the illuminating circuit. So at this point, our charging circuit has charged up our capacitor to 5 volts. Now, we want those 5 volts to discharge at night. So how do we do that? So we do that by using a transistor. And so what the transistor does, it acts like a switch. And so when it sees a voltage drop from a higher voltage of the voltage after a voltage drop, then it'll let the voltage that's up here travel through the transistor to the output. So the idea is that we have the voltage of the capacitor at the collector pin of the transistor. And then we have the voltage of the solar panel flowing into the base pin of the transistor. So what happens is that at nighttime, the solar panel is going to switch from 9 volts to 4.4 volts because of our resistor hooking up into the base. So when that happens, the 9 volts drops to 4.4, and this says, hey, now the voltages here are equal. So let's let it flow. So at nighttime, we get these 5 volts to flow through and become, with the voltage drop, becomes 4.4 volts going out into the LED and the charge monitoring circuit. And so, some of the other components that we have in this is a potentiometer, which is a device that lowers and increases the resistance of the circuit. So this one is about 0 to 25 kiloohms is the range of which we can use for resistance. The second one is we have a current amplifier in there. So basically, we have the 5 volts running into a diode, which emits a constant 0.7 volts, which runs into the current amp and gives us with that constant voltage, emits a also constant current. And so with that current, goes into the LED. So no matter when the capacitor is discharging, it decreases in voltage. But because of this current amplifier and the diode, the LED will not increase or decrease in how much it lights. Only if you change the potentiometer will the LED change its light. And so the last thing that we have is a switch. What the switch does is that when we turn it on or off, is basically you'll see it as a result in the LED that it'll either shine on or it'll shine off completely.
Alright, so what we have here is our illumination circuit, and this is our LED that will light up once the capacitor, which has 5 volts, discharges. So what happens is that once it turns at night, the voltage from here will read 4.4 volts with the voltage across, and this will turn on the transistor, and this will all current and the voltage will pour into this rail right here, as you can see where my finger is. And then from there, we have a diode to emit a constant 0.7 volts going into the potentiometer and this current amplifier. And with this, we can increase the resistance going into the LED by turning this knob left and right, and it increases and decreases how high the light of the LED goes. But no matter how much the voltage across the capacitor changes, the LED will stay the same brightness because of the current amplifier. And down here you'll also see a switch which is connected to the back across to the potentiometer, and with that we can turn the white LED on or off.
This is our charge monitoring circuit. The purpose of the charge monitoring circuit is to light one of the 2 LEDs depending on the capacitor voltage. If the capacitor is more than 50% charged or greater than 4 volts, the green LED will illuminate. Conversely, if the capacitor is less than 50% charged or less than 4 volts, the yellow LED will illuminate. When lit, the LED will flash for about 0.1 seconds every 2 seconds.
Okay, so the third part of our circuit is to create a charge monitoring circuit. So basically, the idea behind the charge monitoring circuit is to keep track of how much our capacitors discharge voltage into the white LED, or the illuminating circuit. So, the basic idea that we have here is that the LED will run between 5 volts and 3 volts, which is the top and the lowest point in which the LED will be lit. So, how we keep track of this is that we have an above 50% qualification and a below 50% qualification. And so basically the idea is that if for our comparator and timer, when the voltage is above 50%, it's actually, the voltage is above 4 volts, which is halfway between 5 and 3. But if the voltage is below 50%, then that is when the voltage is below 4 volts. So basically we have some similar things that we used in the last circuits. We have a comparator and a transistor, which are the same ideas. They act as switches, or they turn on and off when the voltage is has a certain value based on V plus and V minus. But the third thing that we introduced into this circuit is the timer. So part of our project was to have the LEDs flash at a certain point, at 100 milliseconds is how long the flash is at every 2 seconds. So, the basic way that a timer works is that the output of the comparator and the transistor goes into the timer, and so the timer reads what is going on, whether or not it wants the comparator to express if it's over or under 4 volts. So, let's say the timer, for whichever one it reads, okay, it's over 4 volts, I need to express this to the LED. So, we have it set up with resistors and different pins to express that we want it to go for 100 milliseconds every 2 seconds. So, it does that, runs all the way through the timer and into the LED, which is connected to ground. And so, for the entire time that the 5 volts is between 5 and, the capacitor is between 5 and 4 volts, the green LED will be on. And then, when the capacitor is between 4 and 3 volts, then the yellow LED will be on.
This green LED and this yellow LED down here are the way that we can tell if the capacitor is above 50% or below 50%. So, what happens is that if the capacitor is discharging in between 4 and 5 volts, this comparator here will read that the V plus is larger than V minus, so it'll read an output which goes into this transistor and then up into this timer. Now this timer is rigged with all these transistors you can see, resistors, not transistors, which go into this transistor, as you can see here, with the output going to this green LED. So this will blink at a certain time that we set with these resistors from this timer at 100 milliseconds every 2 seconds whenever this comparator has an output between 4 and 5 volts. But once the capacitor reaches below 4 volts, along this rail it'll go down to this comparator, and the V minus will be less than the V plus, sorry. And this will have an output. So this output goes down to this transistor and to these resistors, and goes up to the timer up here. And again, with this timer we have it rigged the same way to blink this LED at 100 milliseconds every 2 seconds, and it goes through this transistor and all these different resistors, and then ultimately the output that goes to this LED is through this transistor right here. And so with these LEDs we can tell whether or not the capacitor is discharged over or under 50%.
This is our flashing beacon circuit. The purpose of the flashing beacon circuit is to flash a red LED briefly for 1 second at 1 Hz when the solar panel is disconnected, i.e. nighttime. Similar to the illumination circuit, there is a switch that can be activated by the user in order to switch the LED on or off.
Now, the last part of our project, which is the extra credit, is the red beacon. Now, again, the red beacon is to flash on at night. So what we have here, we have the red beacon, as you can see here, connected to the same rail with these green wires. Even though it's on a separate breadboard, it's going to be powered on at night through this, over here, PMP transistor. It's the same idea, it just continues on to these 2 rails here, as you can see, with these green and orange wires. So, basically, at night the voltage will pour not only into the illumination circuit, but into this red beacon. So the components that we have in the red beacon circuit are basically a timer, this transistor, and the red LED, and the switch. Now, again, we have the timer set up with the resistors to shoot the voltage and the current to the LED at a certain time, but it's different than the others. We have this one set up to flash for 100 milliseconds every second. So it flashes for the same amount of time, but twice as fast. And also, we have the output connected to a transistor to the base, powered by these 2 rails, which are again powered by the capacitor over here. And then the emitter goes through the LED, which then goes to this switch, which is connected to ground. So if we turn this switch on or off, it determines whether or not this red LED will be on or off. But anyways, so that is all the components of our electronics projects.
We hope you enjoyed watching this video.
Yes, we hope you enjoyed it.
Once again, I am Bryan.
And I am Ryan Hopkins.
Thank you.